The Eiffel Tower. Why architects still look up to it. Most people recognize the Eiffel Tower before they understand it. Its outline is everywhere. On postcards, in movies, on clothing, in advertisements, and in small souvenirs sold far beyond France. 4 legs spread across the ground. 2 broad platforms interrupt the climb. The frame narrows until it becomes a thin point above Paris. Because the image is so familiar, the tower can begin to feel simple. It is not. To understand the Eiffel Tower, we have to stop treating it as a symbol and begin treating it as a problem. A 300-meter problem. How do you build higher than anyone has built before? Using 19th century tools. How do you keep the wind from controlling the structure? How do you make 4 enormous leaning legs meet accurately, hundreds of feet above the ground? How do you move thousands of visitors through a frame that narrows as it rises? And how does a temporary exhibition structure become the permanent image of a city? Those questions give the tower its real meaning. Architects do not continue to admire it because it is tall. Many buildings are taller now. They admire it because one clear idea connects the structure, material, construction, public experience, and later, life of the building. The legs spread because the tower needs a wide stance. The ironwork remains open because wind must pass through it. The frame narrows because the forces change as the tower rises. The platforms hold the 4 legs together and create level space inside a body that is always leaning inward. Rivets connect thousands of separate components. Foundations, hidden below the ground, carry everything above. Nothing is accidental. The form is the record of the problems being solved, and before the tower could solve any of those problems, someone first had to believe that a structure of this scale was possible. France was preparing for the Exposition Universelle of 1889, a World's Fair that would also mark the 100th anniversary of the French Revolution. The organizers wanted a monumental entrance that could announce the event across Paris. The competition called for an iron tower 300 meters high, roughly 1,000 feet. No human-made structure had ever reached that height. Until then, the tallest landmarks were usually cathedral spires, civic domes, towers, and bridge piers. Each belonged to a familiar type. A 300-meter iron tower did not. It asked architecture to become almost pure height. The first important idea came from 2 engineers in Gustave Eiffel's company, Maurice Koechlin and Funmile Nouguier. In 1884, they developed a concept for a giant metal pylon. Their drawing showed 4 open lattice supports, separated at the base and joined as they rose. The early proposal looked more like infrastructure than architecture. That was not a weakness. It revealed where the idea came from. Eiffel's company had designed large metal viaducts. Their bridge piers had to carry heavy rail lines across deep valleys while remaining stable in strong wind. Those projects taught the firm how to create tall, open frames, how to use diagonal bracing, how to distribute force through slender metal members, and how to fabricate complicated parts before sending them to site. The Eiffel Tower began as bridge knowledge turned upright. But a bridge pier is not automatically a public monument. The engineers brought in Stephen Sauvestre, the company's architect. He refined the appearance and added elements that made the proposal more understandable and inhabitable. Great arches between the legs, public floors, enclosed spaces, and a more resolved top. That change established the basic partnership behind the building. Koechlin and Nouguier formed the structural concept. Sauvestre shaped the public and architectural expression. Gustave Eiffel recognized the project's potential, supported it, helped secure the patent, fought for the commission, arranged financing, and placed the capacity of his company behind it. The tower is connected to one famous name, but it did not come from one mind. It emerged from cooperation between engineering, architecture, business, drafting, fabrication, surveying, and construction. That collective origin matters because it explains the logic of the building. The Eiffel Tower was not first imagined as an isolated sculpture and then forced to stand. It developed from knowledge about material, force, fabrication, and public use. The design was bold, but it was not careless. Paris did not immediately see it that way. Before the tower was complete, writers, painters, sculptors, and architects protested against it. They knew Paris as a city of stone facades, domes, boulevards, churches, palaces, and carefully ordered public space. The tower looked like an industrial skeleton placed into that setting at an impossible scale. They saw scaffolding where the designers saw structure. They feared that one object would dominate the city and reduce everything else to background. Their concern was not entirely wrong. The Eiffel Tower did change the visual scale of Paris. What the critics could not know was that its industrial character would become the source of its beauty. The building did not hide the material. It did not wrap the frame in stone. It did not cover the connections with a decorative skin. Its structure became its appearance. This is the first major reason the tower still matters to architects. Many buildings separate what they look like from how they work. Columns disappear behind walls. Beams hide above ceilings. Bracing is concealed inside finished surfaces. The public sees an exterior image while the forces remain invisible. The Eiffel Tower does the opposite. The legs, girders, braces, plates, and rivets are all visible. The pattern that keeps the frame stable also creates the visual rhythm. The silhouette comes directly from the way the structure carries wind and weight. Engineering does not sit behind the architecture. Engineering becomes the architecture. That relationship begins with the material. The tower was built from puddled iron, a type of wrought iron that could be rolled into plates and simple sections, then connected into larger, built-up members with rivets. Today, exposed metal frames are familiar. In the 1880s, using iron for the tallest monument in the world challenged both construction practice and public expectation. Stone represented permanence. It belonged to cathedrals, memorials, palaces, and civic institutions. Iron belonged to bridges, train sheds, factories, machines, and markets. The Eiffel Tower asked the public to accept that an industrial material could carry civic meaning. The choice was not only symbolic, it was necessary. A stone tower of similar height would have become enormously heavy. Masonry performs well in compression, but every level adds more load to the structure below. The walls must grow thicker, the foundations larger, and the entire tower heavier as it rises. Iron allowed the designers to place material only where the structure needed it. Instead of a continuous wall, the tower could use separate members connected into deep frames. Diagonal bracing could prevent those frames from changing shape. Large open areas could remain empty. The void was not wasted space. It was part of the structure. A flat plate can bend easily. Spread the material apart, connect it with diagonal members, and the frame gains depth. That depth makes it much harder to deform. The Eiffel Tower is strong, not simply because it contains a large amount of iron, but because that iron is arranged intelligently in 3 dimensions. From a distance, the tower seems almost weightless. Up close, the members are substantial. Plates overlap. Angles combine into larger sections. Diagonal bars cross in layers. Rivets form long rows across the joints. The metal frame alone weighs about 7,300 tons. The tower does not remove weight. It organizes weight so efficiently that the result appears light. That structural logic becomes easier to understand. If we follow the building from the ground upward, everything begins below the pavement. The site stands close to the Seine, and the soil conditions were not the same beneath all four legs. On the riverside, water complicated the excavation. Workers used watertight metal caissons and compressed air so they could continue digging below the water level. This technique came from bridge construction. Large masonry and concrete foundation blocks spread the loads into the soil. The iron legs were anchored into those blocks so that gravity, wind, and overturning forces could pass safely into the ground. Visitors rarely see any of this. The part of the tower that appears to escape the earth depends entirely on the part buried beneath it. Once the foundations were ready, the four legs began to rise. They start far apart, forming a square, roughly 410 feet on each side. Each leg is not one solid column. It is a large, built-up lattice pier composed of major iron members tied together by smaller braces. The wide base serves two purposes. First, it creates a stable footprint. A tall structure subjected to wind needs leverage against overturning. Spreading the supports gives the frame that leverage. Second, it allows the loads from the upper tower to divide among four large foundation points. The legs then curve and lean inward. That shape is one of the tower's most recognizable features, but it is not merely visual. Wind becomes a governing force at this height. A solid wall would present a huge surface to the air. The Eiffel Tower's open lattice allows much of the wind to pass through. The pressure that remains enters the braced frame and travels through the legs toward the foundations. The frame is widest and deepest near the bottom, where the bending effects are greatest. As the tower rises and the required structural depth decreases, the body becomes narrower. The curve, therefore, records the changing force. The tower looks graceful because the structure becomes more efficient as it climbs. The four legs do not work alone. They are connected by horizontal girders and platforms. The first platform is the most important of these connections. During construction, the lower legs rose separately from the four corners of the site. Each one leaned inward. If small errors accumulated in their position, the main girders of the first floor would not meet correctly. This created one of the most critical moments in the entire project. Four separate structures had to become one. Temporary timber scaffolds, sandboxes, hydraulic jacks, and careful surveying allowed the builders to make fine adjustments. The legs were brought into alignment. The first level, girders connected them at the correct height and angle. Once that platform closed, the tower changed structurally. The four independent legs began acting as one coordinated frame. The first platform also solved an architectural problem. The main body of the tower is always leaning inward, but people need horizontal space. Restaurants, circulation paths, observation areas, and machinery require level floors. The platform creates stable human ground inside a sloping structure. That is why it cannot be understood only as a viewing deck. It is a structural tie, an occupied floor, and a transition between the enormous base and the narrowing tower above. The second platform repeats the same principle at a smaller scale. Above it, the tower becomes a more concentrated vertical shaft. This sequence gives the building a clear order. Broad ground first level, narrower second level, upper tower, summit. The platforms allow visitors to understand the height in stages rather than as one uninterrupted climb. The great arches between the legs serve a different role. They contribute to the composition, but the primary loads still travel through the legs, girders, and bracing. The arches help the eye read four separate supports as one monumental gateway. They create a center. They frame the approach. They make an engineering frame feel like a public entrance. This is where Silvestra's architectural contribution becomes visible. The tower did not need to imitate a stone building, but it needed to become understandable to people. The arches and platforms made the frame legible as a place. Then came the problem of movement. How do thousands of visitors travel through a tower whose legs are curved and inclined? A normal elevator moves through a straight, vertical shaft. The lower Eiffel Tower does not provide one. Engineers had to develop elevator systems that could follow the geometry of the legs and safely carry large numbers of visitors upward. In 1889, elevators were still a relatively new experience for much of the public. Here, they were not simply a convenience. They were part of the building's central idea. Without elevators, the tower would have remained an object admired mainly from below. With elevators, height became inhabitable. Visitors could enter the frame, pass between the braces, and watch Paris change beneath them. At ground level, the tower dominates the person. Inside the elevator, the person begins to understand the tower. Members that appear delicate from far away pass close to the cabin as heavy construction. Openings reveal fragments of the city. The four legs slowly move closer together. At the platforms, the relationship changes again. The first floor feels broad enough to form a small elevated district inside the iron. The second is tighter and more exposed. At the top, the public space becomes a narrow point surrounded by air. The tower turns ascent into a sequence of experiences. This is the difference between an engineering object and architecture. The structure does not merely survive force. It organizes human movement, perception, and memory. The tower also made a new view of Paris available to ordinary visitors. From the upper levels, boulevards become lines, blocks become patterns, domes and monuments that dominate their neighborhoods become smaller parts of a wider city. The Eiffel Tower changed the skyline from below, but it also changed the way people understood the city from above. By this point, the logic of the finished design becomes clear. The foundations negotiate with the soil. The wide base resists overturning. The open lattice reduces wind pressure. The curved legs follow changing structural demand. The platforms tie the frame together and create occupied space. The elevators convert height into public experience, but a clear design is not enough. The next question is how 19th century builders turned that design into reality with enough precision to make 18,038 separate iron parts meet correctly. The answer was preparation. More than 5,000 workshop drawings translated the tower into buildable information. Components were traced, cut, drilled, and preassembled in Eiffel's workshops at Levallois-Perret before being transported to the site. This process reduced uncertainty. The holes were drilled before arrival. Pieces were checked in the factory. Sections were organized into manageable units. Components that failed inspection could be corrected before they reached the growing tower. The site was not expected to invent the building as it rose. It followed a system. That system allowed the entire project to be completed in 2 years, 2 months, and 5 days. The speed is extraordinary, but speed was not the goal by itself. It was the result of coordination. Every drawing had to communicate clearly. Every part had to be identified. Every hole had to align. Every team depended on work completed by another team. A small mistake near the base could become a large problem higher up. The tower, therefore, required control of tolerance. On paper, lines meet perfectly. On a construction site, material varies. Temperature changes dimensions. Foundations settle. Workers need room to assemble pieces. Equipment introduces limits. The task was not to pretend those conditions did not exist. The task was to create a process that could absorb them without losing the geometry. Surveying, temporary supports, hydraulic adjustment, and prefabrication all served that purpose. The rivets completed the connections. About 2.5 million rivets were used across the tower. A rivet was heated, inserted through aligned holes, and formed into shape while hot. As it cooled, it contracted and pulled the plates tightly together. Riveting required teamwork. One worker heated the rivet, another handled it, another held it in position, another formed the second head. The operation was loud, hot, repetitive, and physical. It is easy to admire the tower as an abstract calculation and forget the labor that made the calculation real. Workers stood on exposed iron, lifted components, aligned plates, heated rivets, swung hammers, and repeated the process thousands of times. The precision of the tower depended on the precision of their work. That fact changes the meaning of the monument. It is not only a record of famous designers, it is also a record of people whose names are not attached to the building, but whose decisions still hold it together. Every row of rivets connects drawing to hand. The triangular bracing shows the same relationship between simple principle and repeated labor. A four-sided frame can distort. Push it sideways, and it can collapse into a diamond. Add a diagonal member, and the geometry becomes far more stable. The Eiffel Tower repeats this principle throughout its body. The diagonals prevent the frame from racking, distribute wind loads, and connect larger members into deep structural units. They also create the visual pattern of the building. Large triangles contain smaller ones. Heavy members frame lighter members. Layers overlap. The density gradually changes as the tower rises. The structure is therefore both technically necessary and visually rich. You can see through it, but you cannot understand all of it from one position. From a distance, the silhouette is clear while the connections disappear. Up close, the rivets and plates become visible, while the summit moves beyond the field of view. From inside the frame, Paris appears through layers of iron. The tower cannot be reduced to one image, and the more clearly its mechanisms are understood, the more impressive it becomes. Explanation does not destroy the effect. It deepens it. We can follow the load from the upper frame into the legs. We can see why the base spreads. We can understand why the lattice remains open. We can reconstruct how the first platform connected 4 rising supports. We can see how workshop precision made rapid construction possible. The building becomes more remarkable because the difficulty becomes more specific. The tower was not designed to remain perfectly motionless. No real structure is. Wind causes movement. Heat causes expansion. Cold causes contraction. Loads shift. Materials respond. Sunlight heats different faces of the tower during the day, causing small, uneven expansions. The summit can move slightly as the warm side changes. Seasonal temperatures can also alter the total height by a small amount. This is not failure. It is controlled material behavior. Good design does not force a material to behave unnaturally. It understands the movement and keeps it within safe limits. The open frame makes this idea visible. The long members respond to wind and temperature, yet the overall system remains stable. The tower survives because it can move a little. It also survives because people protect it. Iron corrodes when exposed to water and oxygen. Paint therefore, performs structural work. It creates a protective barrier between the metal and the weather. The tower has been repainted many times, traditionally on a cycle of roughly 7 years. Its color has changed through reddish, yellowish, and brown tones. Different shades have been used across the height to help the structure appear more even against the sky. For visitors, paint is appearance. For the building, paint is defense. This leads to the next part of the tower's logic. Construction gave it form, but maintenance gave it time. No building becomes permanent simply because the opening ceremony ends. Inspections, repairs, new coatings, elevator work, safety improvements, and updated public spaces all continue the original project. The Eiffel Tower remains alive because later generations repeatedly decide that it is worth caring for. That care became especially important because the tower was not originally guaranteed a long future. Its concession lasted 20 years. It had been built for an exhibition, and dismantling remained a possibility after the agreement expired. The structure had proven that it could stand. Now it had to prove that it could remain useful. Gustave Eiffel encouraged scientific work on the tower. It became a place for meteorological observation, aerodynamic research, and experiments in wireless communication. Its height made it valuable as an antenna. Radio transmission eventually gave the tower practical and strategic importance. This saved it. The irony is striking. The structure had been criticized as an unnecessary machine. Its usefulness as a machine helped preserve it as a monument. That survival was not separate from architecture. It completed the building's meaning. A temporary exhibition object became a scientific platform, a communication structure, a public observatory, and finally, a global symbol. Those roles accumulated over time. The antennas changed the summit. The elevators changed. Public spaces were rebuilt. Lighting altered the nighttime appearance. Security changed the ground around the base. Yet, the essential idea remained visible. 4 supports rise, connect, and taper, because the identity of the building rests on structure and proportion. It could absorb new layers without losing itself. Paris changed as well. At first, the tower appeared to violate the city. Over time, it became a point through which the city could be understood. It appeared above roofs, at the end of streets, between buildings, and across the river. The object, once accused of destroying Paris, became one of the main ways the world recognized Paris. Its open construction helped that transformation. The tower does not behave like a solid wall in the skyline. Sky remains visible through it. Fog can erase the top. Rain darkens the iron. Sunlight catches some members and leaves others in shadow. At night, the frame becomes light against darkness. The tower shares space with the atmosphere. That is why it can appear powerful without feeling entirely heavy. The broad base controls the ground. The upper frame becomes increasingly fine. Material is gradually reduced until the tower ends as a narrow line. It appears to transform weight into height. This connects the Eiffel Tower to a much older architectural ambition. Gothic cathedrals used pointed arches, ribs, buttresses, and pinnacles to make stone rise. Domes turned massive construction into an image of sky. Classical architecture used proportion to control the visual weight of buildings. The Eiffel Tower pursued the same vertical aspiration with iron. It did not reject architectural history. It continued that history in a new material language. This is why the building cannot be described as engineering alone. Engineering explains how it stands. Architecture explains how standing became space, movement, image, public use, and memory. The tower joins those questions into one system. Wind shaped the profile. Structural depth created transparency. Platforms created stability and occupation. Elevators created access. Rivets created connection and texture. Paint created protection and color. Scientific use created survival. Maintenance created longevity. Each solution supported the next. That is the logical strength of the building. It did not solve one dramatic problem while ignoring the others. It connected many practical problems to one clear idea. The result remains easy to recognize and difficult to exhaust. A child sees a giant tower. A tourist sees Paris. An engineer sees bracing and load paths. An architect sees force becoming form, and form becoming experience. A fabricator sees parts. A conservator sees coatings, corrosion, and future work. A historian sees a society learning to accept industrial modernity. The building holds all of those readings at once. That is why it has remained culturally durable. The familiar symbol becomes richer when attention returns to the real structure. Look at the legs and remember the foundation blocks below. Look at the open lattice and think about wind. Look at the first platform and remember 4 separate legs being aligned. Look at the rivets and remember the workers who closed them while hot. Look at the elevators and remember that height had to become usable. Look at the paint and remember that permanence requires maintenance. Look at the antennas and remember that a temporary tower needed a practical reason to survive. Then, the building no longer appears simple. It becomes a chain of decisions. The Eiffel Tower did not prove that every building should expose its structure. It did not prove that every controversial design will eventually be loved. It did not prove that height is always progress. Its lesson is more disciplined. A new material can become monumental without imitating an old one. A practical structure can carry emotional meaning. A bold idea can remain clear while solving construction, use, and maintenance. A temporary building can earn permanence through continued value. And courage in architecture is strongest when it is supported by knowledge. The Eiffel Tower was daring, but it was not reckless. Its form was unprecedented, but its designers drew on years of bridge experience. Its construction was dangerous and ambitious, but it was prepared through thousands of drawings and controlled fabrication. Real architectural courage is not the rejection of constraints. It is the use of constraints to create something that did not exist before. That is why the famous numbers are not enough. 300 meters, 18,038 iron parts, about 2.5 million rivets, roughly 7,300 tons of metal. 2 years, 2 months, and 5 days of construction. The meaning lies in the relationships between those numbers. Thousands of parts became one form. Heavy iron became visual lightness. Bridge engineering became a civic monument. Industrial production became public experience. A temporary exhibition structure became part of Paris. Maintenance became longevity. Engineering became architecture. The tower's greatness does not come from one miraculous detail. It comes from the continuity of the reasoning. The foundations support the legs. The legs answer the wind. The platforms stabilize the frame and support people. The elevators make height accessible. The prefabricated parts make construction possible. The rivets create one body. Scientific use protects the future. Maintenance carries the building through time. Every stage leads to the next. That is why architects still look up to the Eiffel Tower, not because it stands higher than older buildings, not because the past was more capable than the present, and not because fame deserves respect by itself. They look up because the tower shows what happens when imagination is supported by knowledge, when engineering is allowed to shape beauty, and when thousands of precise decisions remain faithful to one idea. The tower does not ask later architects to copy its outline. It asks them to think clearly, understand the material, respect the forces, make structure part of the experience, prepare the design for construction, respect the people who will build it, allow the building to adapt. And remember that permanence is not granted when the last piece is installed. It is earned through usefulness, care, and time. The Eiffel Tower is not the achievement of one heroic figure. Its real story is stronger than that. Two engineers proposed the essential structure. An architect made it publicly legible. Eiffel recognized and drove the opportunity. Designers produced the information. Factory crews prepared the pieces. Site workers assembled them. Scientists gave the tower new purpose. Technicians protected the iron. Paris gradually gave the structure a place in its memory. Many people created one clear form. Many generations completed its meaning. So the next time the Eiffel Tower appears as a familiar outline, do not stop at recognition. See the bridge knowledge inside the tower. See the wind inside the curve. See the soil beneath the legs. See the human use inside the platforms and elevators. See the workshop inside every matching connection. See the workers inside every row of rivets. See the maintenance inside the color. See the future inside the antenna. Then the image remains the same, but the understanding changes. The tower is no longer only an icon. It becomes evidence. Evidence that industry can become culture. Evidence that empty space can create strength. Evidence that structure can become beauty without hiding how it works. Evidence that a temporary work can become permanent when it continues to serve, adapt, and deserve care. That is why, more than a century later, architects still look up to the Eiffel Tower, not because it stands above the city, because every part of its story supports the idea behind it.